Reduction potentials. So reduction potentials are a way of measuring the reduction, the ease of having the reduction reaction occur. And it's relative, just like all of our things are relative to a certain benchmark. This is relativized to the reduction potential, or how easily hydrogen becomes reduced. So hydrogen becoming reduced is set at a benchmark of 0, in this case volts, because we're talking about electrons, we're talking about electricity, and we call that the standard hydrogen electrode, or SHE. So the more positive the potential, the more likely you're going to be reduced. And the more negative the potential, the less likely you're going to be reduced. But again, whenever you're having a reduction and oxidation, you're really looking at two things that are competing for the same electrons. So really, the one that has the higher reduction potential is going to be more likely the one that's going to grab the electrons, get reduced, and the one that has the lower reduction potential will lose those electrons, will lose that tug of war, and end up being oxidized. So the second mnemonic that I'm giving after oil rig or Leo the lion goes grr is P, or positive potential products predominate. That means that the more positive your potential is, your reduction potential, or could be oxidation, the more likely the reaction is going to go as it's written. The more likely the products that are going to be written are going to be the ones that you're going to see. So the more positive potential, the more positive the reduction potential, the more likely that substance will be reduced. The higher it is, the easier it will be reduced, and the less positive it will be oxidized. And the units are volts. Right? And standard just means that it's going to occur at 25 degrees Celsius at one atmosphere pressure. So if I end up being oxidized, that magnitude of that potential will be the same, but the sign will be reversed, right? Because rather than grabbing an electron, I'm giving up electron. That ease of giving up an electron should be the same magnitude. It's just whether I'm gaining the electrons or I'm losing the electrons. So here's an example. I'm looking at silver and copper, and these are the reduction potentials of both of them as listed in a reduction potential table. They're both reduction because they're both gaining electrons. And the number of electrons that they gain is just however much they need to attain being a solid, not being an ion. So as it's measured against hydrogen, silver has an oxidation, a reduction potential of 0.8 volts, meaning it is easier to be reduced than hydrogen, more likely. Copper is also positive, but it's less positive, it's 0.34. So if the silver ion and the copper ion are both competing for electrons from the same source, silver is going to be the one that's going to win out because it has the more positive potential. Right? Notice how we're not saying one's negative, one's positive. It's the more positive potential. They're both positive in this case. So silver has the higher reduction potential because 0.80 is greater than 0.34. So as a result, silver is going to be reduced and it's going to get those electrons, in this case, from copper. So copper will be oxidized. So what's going to happen is that the opposite reaction of this is going to occur. Copper will start out as a solid, lose its electrons, in this case to silver, and become aqueous ions. As a result, the oxidation potential is going to be negative 0.34. So again, the magnitude, the number stays the same. It's just that the sign is reversed. This was positive, now this is negative. So it's reversed from the reduction potential. And this is the oxidation potential because it's the potential for the oxidation of copper. You have to remember that both reduction and oxidation have to occur, right? The reduction reaction has to get its electrons from the thing that is oxidized. So reduction potential is a measure of which reactant is going to be the one that's going to win out. And so in this case, we've established that silver is going to be the one that reduces, and this is the one that's going to be oxidized. So what's going to happen is when I combine these reactions, their reduction potentials will be added together, or rather the reduction potential of one and the oxidation potential of the other will be added. So these just get added together. So my overall potential for my reaction is 0.46. Then I have to go through balancing, and this is a simple one because this doesn't have any oxygen or hydrogen. So I have to run this reaction twice in order to grab the electrons that the copper is losing. So my overall reaction is going to be 2 silver plus copper solid yields copper 2 plus 2 silver. Notice that the reduction potential is not multiplied by 2 here. I'm not multiplying this by 2. This was a mistake. So whenever you're doing overall potentials, go ahead and add these two together at the beginning so that you're not tempted to accidentally multiply this by 2 and then have a false sense. The reason why the reduction potentials aren't multiplied, like say in enthalpy or calories or things like that, is because this is not a measure of how many electrons are being transferred. It's a measure of the strength of the reactants to begin with, right? And that strength of the reactants doesn't depend on how many of the reactants are. It's just assuming a one-to-one matchup between the two reactants, and that 0.8 and 0.34 are a measure of the strength of their nuclei, which shouldn't matter how many of them are there, because it's not like they're teaming up to pull electrons away from, one poor copper. It's just that every time copper loses 2 electrons, 2 silvers are able to gain those 2 electrons. So again, the reduction potential is a measure of the strength and not dependent on stoichiometric ratios. Here's another example. I have zinc and I have aluminum ions, and these are their reduction potentials. They're both negative. Still, the more positive potential predominates. So because the zinc reduction potential is more positive, it's closer to 0, it's going to be the reduction reaction. This will be the oxidation reaction, and so it will flip. So zinc will still be reduced, and it will have a reduction potential of negative 0.76. And aluminum will be oxidized, which means that it will have now a positive 1.66 oxidation potential. I add these two together and I get an overall potential of 0.90. And then I do the whole balancing again. I have to multiply this by 3 and this by 2 because this is losing 3 electrons and this is only gaining 2 electrons each time. So my overall reaction is 3 zinc ions plus 2 aluminum atoms yield 3 zinc atoms and 2 aluminum ions, and the overall potential is 0.90. This positive also, so when we say positive potential products predominate, it also refers to this. It's saying because this overall potential is 0.90, what's going to happen is that the products of zinc as a solid and aluminum as an ion are much, much more likely to occur than the reverse reaction of aluminum solid and zinc ions being created. So if zinc plus 2 and aluminum are put together, the aluminum will dissolve and the zinc will be coming out of solution. So I will see that as a reaction. So if you recall from first trimester when we did our more characteristic chemical reactions, we had a situation in which we had aluminum in zinc nitrate. And in that case, we totally had a reaction that occurred. It was fairly strong and you saw the aluminum start to become more mushy, right? Whereas when you had zinc in the aluminum nitrate solution, nothing happened. And here's why. Because if I have aluminum being reduced, that would have a reduction potential of negative 1.66. And if zinc was oxidized, its reduction potential will be reversed to become positive 0.76. So my overall redox potential is going to be negative 1.66 plus 0.76, or negative 0.90. It's not spontaneous. So if I put zinc solid in an aluminum nitrate solution, an aluminum plus 3 solution, nothing's going to happen. You can leave it there for a really long time, nothing is going to happen. Unless, and this is true of all non-spontaneous reactions, unless I put energy into the system equal to or more than how non-spontaneous the reaction is. So in this case, if I add at least 0.90 volts of energy, I'm constantly supplying it, right? Remember that non-spontaneous means I constantly have to supply that energy, or I'm just going to start doing the spontaneous reaction. If I constantly supply that to it, then I can run the non-spontaneous reaction. This becomes really important when we start talking about batteries, right? So batteries are the spontaneous reaction, but batteries run out. So now we have this really cool thing where we have rechargeable batteries. What do you have to do with rechargeable batteries? You have to plug them into the wall so that you run a current, and the current allows the non-spontaneous reaction to occur. So I regenerate my reactants from my products, and I can start the whole process all over again. So after this, we're going to be talking about galvanic cells, which is just batteries, and we'll be able to think about that in terms of our reduction potentials.